All right. So next we will start talking about the single source shortest path problem. So I think it's a more, it's easier to understand. I mean, in terms of the nature of the problem. So it's like what this problem is about. Then I guess the shortest path problem is more straightforward to understand because it relates to a everyday problem that we find a path on the map, for example, right? We want to navigate. We want to find the shortest distance path from our destination, right, to our destination. So this single source shortest path problem is also a algorithm based on the weights, okay, based on the weights of the data of the graph data structure. So it's can think of it from the concrete example, the concrete problem to find the shortest path route from between cities, right? And if we want to represent a map with some data structure, then of course we need to represent, for example, the cities use some vertices, right? Or we can use any adjacent intersections, right, of the highways as the vertices, right? It can be any points on the map that connect to different passes as vertices. So I think it's it makes sense to, first of all, it makes sense to represent the problem with a graph data structure, right? And also the problem itself is easy to define in terms of a graph algorithm, in terms of a graph problem. Okay, so let's say if we zoom in a bit to a smaller region, and actually each intersection on the map can be represented by a vertex in a graph, right? And a segment of road connecting the two intersections is an edge, right? So that is a very reasonable assumption, right? So the road connecting the intersections is an edge, but that road, that edge must be weighted, right? Because longer roads, of course, takes longer time to travel, and also if we take into the traffic into consideration, it will be a more complex issue, right? So if we start with some simple assumption, we can basically use the length of the segments of the road in terms of the weights, okay, to be represented by the weight of the edges, okay. And also the graph is directed, okay. That is also another assumption. So because we will know that some roads are two-way, right? Some are one-way roads. So that is also a reasonable assumption. Okay. So you can see this type of problem, the shortest path problem, is more advanced because now we consider the directions. It's not just about connectivity, but also it's about how the direction is, which direction it is, and also how much weight it is. Okay, so it's a more complex problem for now. All right, so let's look at how this problem is defined. Okay, so here's a bunch of terms, but actually don't be afraid of it. It's actually a very straightforward definition. So first of all, it's defined on the weighted and directed graph. All right, and we have a weight function. So far everything is pretty similar to the minimal spanning tree problem. And the problem is that we want the weights of a path. Okay, right? We want a path. We actually consider the weights of a path, and a path is just a collection of vertices from V0, V1 to Vk. Okay, And the weight of a path is defined as the sum of the weights of its constituent edges. So for this particular path, the constituent edges actually refer to V0 to V1, that is one edge, right? And also V1 to V2, right? And then also V3 to V4, and the last one should be VK minus 1 to VK. So if we like put those edges in the collection into a set, and these are all the constituent edges. And if we sum up the edges for all these edges, then that will be the weights for the path, the total weight of the path. Okay. So let's also assume let's also define the so-called shortest path weight. Okay. So the shortest path weight is a quantity, it's a number, okay, it's a single number. Let's indicate it by this delta between u and v. So this shortest path weight between two vertices from u to v is the minimal value among all the paths, among all the weights of the paths, right? So if there is a path from u to v existing, right? So that is the first condition. So if u to v is reachable, right? If v is reachable to v, then we can go from u to v, right? That's our assumption. So if in that condition, then we need to go through all the possible paths and find the weight for each path, and then find the minimum among them. And that quantity is the so-called shortest path weight delta. Okay. But what if there's no path connecting the two vertices? What if there's no connectivity? Then we will define the delta of the shortest path weight delta to be infinity. Okay, so I think this definition is also very straightforward, right? Because we want to define the problem in a formal way, we will need to use some mathematical language here. All right, so that's how the shortest path weight is defined. And again, lastly, the shortest path can be is not necessarily unique. Okay, the shortest path from u to v can be any path as long as the weight of it is the shortest path weight, right? As long as we know the shortest path weights, what is the minimal weight of it, and as long as we find a path that has the shortest path weights, then we can call it a shortest path. Okay, so that quantity, the paths that have such a minimal weight is not necessarily unique. All right. So lastly, today we can talk about the relationships of this shortest path problem to the elementary algorithm, breadth first search over a graph. Okay, because in the breadth search, BFS, in the breadth first search, we also talk about a shortest path algorithm. We also talk about the path between two vertices, right? But BFS defines a shortest path basically on the unweighted graphs. Remember, we have unweighted graphs. We don't consider the weights, right? But it's unweighted. That also means that all the weight has the same weight. We can think of it as a unit weight, right? Each path has the same weight, which is length 1, for example. So the shortest path in BFS actually, it's actually defined in terms of the number of edges, right? Remember, in the shortest path, in a BFS, if we start from the source vertex S here, right? And then we will search the adjacency vertices, which is R and W first, which makes the distance from R to S to 1, right? The distance from W to S is also 1. And then we go one step further, which we search the T, X, and V. And these three vertices, they all have equal distance, which is 2. right, from their parents, from the source vertex. And the next level would be U and Y. They are actually 3 edges away from the source vertex. Okay, so BFS also sort of computes the shortest path for each vertex, but the difference is that the distance here is not defined in terms of the weights, but in terms of the number of edges connecting the 2 connected vertices. So in but in the chapter that we are here when we talk about the shortest path problem, we are not talking about the number of edges, but rather it is the total weight of edges. Okay, so we are really talking about the weighted graphs. Okay, so these 2 are quite different. Okay, kind of similar, but still quite different. Okay, and we can before we introduce the problem for the next Thursdays, I think we can finish the one for these couple of slides. All right. Okay. So there are several variants of the shortest path problems. So we will only focus on the single source shortest path problems, which means there's just one source vertex. We only consider one source vertex. That is, given a graph, we want to find the shortest path from one given source to each vertex. Okay, and we need to compute the distance, the shortest path for each vertex in the graph other than the source. We need to consider the shortest path for it. Right. So there are other variants like a single destination, right? So that is basically reverse of the single source, right? We determine the destination and we need to consider all possible different sources. And there's a second one, which is a single pair, which I think is a easier problem because we determine the source and the target, the source and the destination, and we just want to find a single pair of it. And the other one, all pairs, which apparently is more complex because you need to enumerate over all possible pairs of combinations. Okay. All right, I think I can leave the remaining part to the next lecture because it goes into the details of the problem, and there will be some basics about negative weights and about the cycles and about how the shortest paths are represented. And we will basically start with the relaxation procedure, a basic operation of finding shortest path problems. And then we will introduce 2 types of algorithms, which is Bellman-Ford and Dihus-Strauss algorithm. Okay, so let's focus on, I will leave this content to the lecture on Thursday. And for the next week, yeah, we're gonna cover the rest part. We're gonna cover the NP complete problem, and we will do a final review. Yeah. All right. If you don't have any questions, I will stop the recording now, and I will, yeah, the homework for the elementary graph algorithms is released. So after this Thursday, I can release the homework for the advanced algorithms.